Hi everybody, my name is Isabeta Rountree and I'm a senior undergraduate research assistant at UAH studying industrial and systems engineering. Today I'll be talking about my research in change management processes and model-based systems engineering that was done with Victor Lopez under the direction of Dr. Dale Thomas. First, I'll talk about where changes come from and how they impact a system, and then I'll talk about current change management methods. I'll introduce model-based systems engineering, and then I'll talk about how we applied it in a case study on a system called Aegis, and then I'll sum it up with my conclusions and future work. So introduction to changes. Where do changes come from? They come from controllable and uncontrollable factors, such as the emergence of new technology or changing stakeholder desires. These changes can increase schedule and cost to a system, which are valuable resources in system development, so they should be managed so that you can better manage those resources. Current change management methods. These current methods involve generally establishing a baseline design, a process to request changes, approval from a change control board, and then rework of engineering analyses based on the change and distribution of that change by document or email. This diagram depicts that traditional change management process as defined by the NASA Systems Engineering Handbook. As you can see, there's 6 parties and 10 different steps with a number of different tasks in between, and some steps even have a couple different boxes for them. So what are the drawbacks of this traditional method? Well, the number of steps and parties involved make it less effective at efficiently addressing changes. The number of people make it difficult to track those changes from person to person, and then it makes it difficult to consistently implement those changes through associated model documentation, which affects the completeness and consistency of that documentation and makes it difficult to maintain and reuse system requirements and design information. And now, what is model-based systems engineering? It's a method of systems engineering centered about developing system models, with one of its goals being replacing documentation with a model. The system model includes the behavioral and structural aspects of a system, and it's usually written in a programming language such as SysML, or a modeling language such as SysML or LML, which is the systems modeling language and the lifecycle modeling language. These models have the ability to be tied in with physics and analyses tools such as MATLAB, Python, and STK. How do you use model-based systems engineering for change management? We use it in a similar process to the one described before, but it has the advantages of having integrated physics analysis, which allows you to dynamically execute your model, faster impactive analysis of requirements and changes because you have that traceability from the top level down in your model expressing all aspects of the system, and then you can automate your document generation to ensure consistency based on model elements. This picture depicts that CubeSat studied change control process, which is basically the previous change management process that we shortened and targeted towards CubeSat using a model-based systems engineering process. As you can see, there's only 5 parties involved and 7 steps, each on their own with tasks involved. It should be noted that this process should be tailored to projects of different sizes, and that a change control board might not always be necessary for projects of a smaller size. So, Aegis is the Alabama experiment for Galactic-ray In-Situ shielding. It's a 6U CubeSat planned as a secondary payload on Artemis II, and we applied the change management process to this project using model-based systems engineering to see how it affected system development. The model for the system was organized using structural, behavioral, and programmatic aspects. The structure was made generally so as to allow the tie-in of physics parameterization so that we could do that automated physics analysis. What were the main benefits? Unchanged physics models did not require adjustment, and in general, the models could be executed by the systems engineer without the discipline analyst. Everything updated was there consistently, and the model generated documentation as well. And then model traceability allowed for change consistency. What were the key findings? Changes are inherent to system development. Changes need to be managed. Physics results allow trade space and figure of merit evaluation, and then less people and integrated physics models reduce schedule impact from change. To sum it up, model-based systems engineering could contribute to designing better systems faster and at a lower cost.